Hi everyone, welcome to the CS SAB webinar series. My name is Ritu Sethi. I'm the Vice Chair of the Standards Activities Board, and I'll be your webinar moderator today. Before we get started, I'd like to take care of some housekeeping items out of the way. The webinar is being recorded, and the slides and the recording will be made available after the webinar. You can ask your questions in the question and answer panel. Today's presenter will answer as many questions as possible following today's presentation. Meanwhile, so today is the topic is overview of IEEE Smart Manufacturing Standards, and our host today is Dr. Shah V, who's the Standards Committee Chair. Before we get started and I offload the topic owner to take it forward, I just wanted to introduce you to the IEEE CS Standards Activities Board mission and the various active standard committees that it foresees. If you see it here, the mission of the IEEE Computer Society Standards Activity Board is to encourage Computer Society members to participate in the standardization activities, as well as to promote the use of IEEE standards and to develop useful products that leverage IEEE standards within the scope of the Computer Society. And moreover, the mission of the SAB is to promote and foster industry participation and engagement as well through standards, but also through other activities. There are different ways in which the SAB accomplishes this mission. It works with other IEEE Computer Society boards and committees to provide standards leadership. It helps to ensure the vitality and success of these IEEE Computer Society standards committees. And it helps to establish new standards activities in response to changes and advances in the computing profession. It also serves as a sponsor for standards activities for which an appropriate existing sponsor does not exist. And then it also works with the other Computer Society boards to identify initiatives for a wider industry participation in Computer Society activities. Here, if you see the list of standards, and it's kind of, today we are covering on the last one on the list here, smart manufacturing. So let me just introduce the presenter for today. Dr. Shah V is dedicated to standardization and strategy analysis of smart manufacturing, digital twin, and artificial intelligence. In the IEEE SA, she serves as the vice chair and member of NESCOM and member of SASB and CAG. In smart manufacturing, she is the chair of IEEE Smart Manufacturing Standard Committee and P2672 mass customization and P2806 digital representation. She's also a member of IEEE SMSC Smart Manufacturing and ISO IEC JWG21 Smart Manufacturing Reference Model, respectively. In digital twin, she is the convener of ISO IEC JTC1 SC41 Workgroup 6 Digital Twin and former AG11 Digital Twin. In artificial intelligence, she is the chair of IEEE P2807 Knowledge Graph Working Group and committee members of ISO IEC JTC1 SC42 in artificial intelligence. We also have Scott Levine with us today, who's with the IEEE Computer Society staff, and he will be helping us with the logistics for the session. And maybe take over a few of the question answer later towards the end. And with that, let's get to today's presentation. Dr. Shah V, the floor is all yours. Thank you.
Thank you. Thank you so much for your introduction, Ritu. I sincerely appreciate that. Okay, so good morning, good afternoon, and good evening, everyone. Thank you very much for joining this webinar on IEEE Smart Manufacturing Standards. My name is Shah Wei. I'm the chair of the Smart Manufacturing Standards Committee. So just as Ritu introduced, I'm currently working on standardization and strategy analysis of smart manufacturing, digital twin, and artificial intelligence. So in this webinar, I will mainly cover 5 sections, starting from a brief introduction of our standard committee. Then I divided our undergoing works into 3 categories, from manufacturing to service. This is our first project, mass customization, and new technologies applied in manufacturing, including machine vision, digital representation, and knowledge graph, and also smart factory assessment and smart logistics. Finally, I will introduce 2 new projects and our future works. Since smart manufacturing is a very broad scope, so I roughly divided our projects, and I will introduce them in details in the following slides. Thank you. So let's begin our journey for the overview and start from who we are. The digital era has really arrived, and there is no denying it. The ongoing digital transformation holds the promise of improving productivity performance by enabling innovation and reducing the costs of a range of business processes. The improvement and the creation of technologies such as big data, AI, and IoT have dictated the pace of society and caused changes in people's routine, habits, relationships, and behavior, among which smart manufacturing will be a game changer for the manufacturing industry. COVID-19 disruption and meeting profitability goals remain the 2 biggest concerns for the manufacturing companies. According to the latest research by Deloitte, more than 17% of manufacturing leaders surveyed are moderately or extremely concerned over the pandemic's ongoing impact on operations, supply and demand, as well as meeting profitability goals. In many ways, this uncertainty emphasizes the growing importance of adopting smart manufacturing initiatives that can drive agility, speed, and performance. Fully connected enterprises allow manufacturers to expand their capabilities, identify cost savings, and better prepare for the post-COVID era. Based on the study of ISO and IEC, smart manufacturing is defined as the manufacturing that improves its performance aspects with integrated and intelligent use of processes and resources in cyber, physical, and human spheres to create and deliver products and services, which also collaborates with other domains within an enterprise's value chains. Smart manufacturing leads to the emergence of agile, real-time, optimized, self-organizing value chains, which are highly adaptive to fast-changing social technical environments. This vision of smart manufacturing is characterized by enhanced product flexibility, new partnerships, new intrinsic built-in product properties, flexible work organizations, fast, functionally safe, and also available communication networks, scalable distributed manufacturing, environmental sustainability, and also value-added services. This dynamic requires appropriate standardized interfaces and harmonized business processes. In 2017, ISO formed a coordination committee of ISO technical committees SMCC, while IEC established the Smart Manufacturing System Committee after a 2-year strategy study. These 2 organizations later established the joint ISO-IEC coordination, agreeing on definition of smart manufacturing, just as I introduced previously, create a joint working group for a reference model, and create a task force to map standards to definition. In ISO-IEC GTC1, the Digital Twin Working Group is built in 2020, which cooperate closely with SDOs in smart manufacturing, smart cities, and smart energy. While here, in IEEE, we first proposed and started a project on mass customization and other project for online detection based on machine vision at the end of 2017 in SAB of Computer Society. Since this area has attracted a lot of attention, the IEEE SMSC was established on September 5, 2019, which is responsible for managing the development of standards within the technical area of smart manufacturing and its associated applications. The scope of our standard committee includes, but is not limited to, the requirements, architecture, models, practices, and technologies that support smart manufacturing. As approved in the first plenary meeting of our standing committee, our committee is composed of a chair, a secretary, a chair, and a technical advisory committee, the standards review committee, and 9 working groups. Among these 9 working groups, one of them focuses on smart services, which is our first topic today, mass customization. 6 of them, which is shown in green, is about how to apply new technologies into manufacturing. These technologies include machine vision, digital representation or digital twin, knowledge graph, TSN, gateways, and industrial AI. Also, we have 2 projects with respect to smart factory, which is shown in purple. In these 2 groups, the smart factory assessment and smart logistics are studied. Although we have 9 ongoing projects, as I introduced in the last slide, I divided them roughly into 3 categories, and other 2 new projects, TSN Gateway and Industrial AI Data, will be introduced in the last part. So let's begin from our part 2, from manufacturing to service, mass customization. Manufacturing and services constitute 2 of the 5 sectors of every country's economy. Depending on the maturity of the economy, they are in terms of employment typically the 2 largest sectors. In mass customization, the profit of manufacturing is shifting from the product to after-sales service, which benefits from data analysis and sharing with ecosystem partners. And this will be our first topic. Companies throughout the world have embraced mass customization in an attempt to avoid pitfalls and provide unique value to their customers in an efficient manner. Readily available information technology and flexible work processes permit them to customize goods or services for individual customers in high volumes and at a relatively low cost. These examples vary from automobile to clothes and home appliances. But many managers at these companies have discovered that mass customization, too, can produce unnecessary cost and complexity. They are realizing that they did not examine thoroughly enough what kind of customization their customer would value before they plunged ahead with this new strategy. Until now, no framework has existed to help managers determine how mass customization they should pursue. In P2672, we try to give a guide of mass customization based on the practical applications in home appliances, computer, cosmetics, high-speed railway, and clothes. After 12 face-to-face meetings and 6 teleconferences since February 1, 2018, this guide provides the definitions, terminologies, operation procedures, system architectures of mass customization, key technological requirements, data requirements, and application related to user-oriented mass customization, and then reference information to manufacturing enterprises for designing and implementing business models of mass customization. With a series of case studies in different verticals, we distill out the customized requirements for both discrete and process manufacturing, main activities along with the product life cycles, core functions to support each activity, relationships with existing management software and IT infrastructure to support mass customization. Specifically, we built a canvas to locate these important activities from the axis of time and logic hierarchy of a factory. Different from mass production, the start point of mass customization is interaction with customers. The data connected from such demand analysis will then be evaluated, which trigger the R&D of a new product or lead to the marketing and sales of an existing product. In order to save research time and cost, modularity is required to create largely independent blocks for building different products and processes. A combination of a limited number of modules permits diversification of the product. In addition, the whole process is transparent to customers. They could easily check the status of the product through the interaction platform. Since the customer already paid a certain number of deposits, the pressure of warehouse is eased, and the product is delivered to the customer directly through integrated logistics from factory to highway. The most interesting and value-added process is in the service part. with the constraints of data privacy regulations and permission of customer for connecting the usage data of the smart product. The data of utilizing this kind of smart product could support remote maintenance, selling the next generation of product to the same customer and people around them, selling a similar series of other products to the customer, or even more, help the ecosystem partners to sell their services or products. These aforementioned activities are further expanded into required and optional functions. The companies could decide which functions they like to realize based on their current software and hardware assets and future investment on mass customization. Turning off the page of mass customization in part 2, we are moving forward to new technology applications in manufacturing. We will first take a look of how machine vision is applied to online detection, and then the buzzy topic nowadays, digital representation or digital twin. Finally, the knowledge graph, which supports the machine readable standards. And the first technology that we want to cover is machine vision. Where human vision is best for qualitative interpretation of a complex, unstructured scene, machine vision excels at quantitative measurement of a structured scene because of its speed, accuracy, cost, and repeatability. Machine vision can replace manual labor for high-intensified, continuous, and precise operations in various production environments like semiconductor, medicine, screen, and so on and so forth, greatly improving work efficiency and quality. The working group P2671 is built to analyze machine vision based on online detection in the factory environment. This working group is chaired by both Dr. Jonathan Chang, who is a very professional manager and engineer in semiconductor industry, and Professor Wu Feng, who is a distinguished expert in management. The corporate members include manufacturers in home applicants, semiconductor, computer, and high-speed railway, as well as famous integrators, research institutes, and universities. These standards specifies through the general requirements of online detection based on machine vision, including requirements for data format, data transmission processes, definition of application scenarios, and performance metrics for evaluating the effect of online detection deployment. With the definition of general flows and the system architecture of the online detection system, the working group defined input, process, and output in sequence. In addition, the function, interoperability requirements, performance, and test methodologies are characterized. To facilitate the use of this standard, the working group also gave 5 examples for IC substrate, thermal grids, IC manufacturing, semiconductor package, and also magnetic tiles. The machine vision detection system is not independent in workshop. It is controlled by mass, and then the generated real-time and long-term data are feedback to mass, SPC, and DMS. In this case, the working group established the system architecture from the perspective of time sequence and the hierarchy inside a workshop. In particular, for the input system, the image acquisition is transmitted through DCP interface, and the input is subject to condition constraints requirements, production detection requirements, and also image acquisition requirements. After the input, the signal will be processed through image processing, feature extraction, and discriminant analysis under the constraint of consistency and detection speed. Finally, the output will be transmitted to mass and SPC. Escape rate and false alarm rate are defined to test the efficiency of the detection system. So this is about the machine vision. And next, we are going to talk about the project on digital representation. As discussed in ISO IEC GDC1 SA41 Working Group 6 Digital Twin, a digital twin is a digital representation of a particular physical entity or a process with data connections that enable convergence between the physical and digital states at an appropriate rate of synchronization, has the capabilities of connection, integration, analysis, simulation, visualization, optimization, and finally, provides an integrated view throughout the life cycle of the physical entity or the process. Although the concept originated earlier in 2002 by Michael Graves, University of Michigan, the first practical definition of digital twin originated from NASA in an attempt to improve physical model simulation of spacecraft in 2010. Digital twins are the result of continuous improvement in the creation of product design and engineering activities. An example of digital twins in the use of 3D modeling to create digital companions for the physical objects. It can be used to view the status of the actual physical object, which provides a way to project physical objects into the digital world. Here, the digital twin is meant to be an up-to-date and accurate copy of the physical objects, properties, and states, including shape, position, gesture, status, and motion. A digital twin can also be used for monitoring, diagnosis, and prognosis to optimize asset performance and utilization. In this field, sensory data can be combined with historical data, human expertise, and fleet and simulation learning to improve the outcome of prognostics. Here in IEEE 2806, we try to define the digital representation in a factory environment. The corporate members are from high-speed railway, computer, and home appliance manufacturers. Integrators for both discrete and process manufacturing also join this working group. This standard will define the system architecture of digital representation for physical objects in factory environments, including the important components, required data resources, and basic establishing procedure of digital representation in factory environments. At the beginning of the study, we try to give a conceptual model of digital representation in factory environments. In particular, the real-world entities included physical objects such as production materials, parts, semi-finished products and final products, production components and equipment units, production lines and workshops, warehouse and factories, plant facilities, and also logical objects such as production process and organizations, work shifts and teams are exempt. Such a system architecture provides a systemic approach and a solid technical foundation to represent the production environment consistently and increasingly holistically for enabling the next generation of smart manufacturing applications. This digital representation system architecture takes into account the latest development trend of technologies and the latest thinking of advancing the digital transformation in the manufacturing space. As a general architecture for the digital representation of factory environment, it intends to support the full life cycle of the production process, as shown in the middle here, covering the product phase, which include the product design and engineering, the production phase, which include the manufacturing process of the products, and also the service phase, that is the distribution and delivery, operation, maintenance, and service of the product. If we want to be complete, it also covers the end-of-life phase. This includes the termination of operation of products and their subsequent disposal and recycling. As a general architecture, it seeks to abstract common characteristics and common constructs and elements to provide broad applicability across industries, that including discrete manufacturing, such as automobile, continuous process manufacturing, such as the oil and gas industry, and batch manufacturing, such as the pharmaceutical industry. It also covers production environments, such as various forms of electric power generation plants. While we are seeking broad applicability, this general architecture also seeks to allow flexibility and extendability so that it can be adapted to support use cases under various usage scenarios, with each of the three major types of industries. This digital representation system architecture provides a common technical language and terminology which concise and consistent semantics with which to communicate ideas and the concepts of digital representation of factory environments within the communication of the stakeholders, within and outside an organization, technology and solution providers or customers alike. It also provides common architecture constructs and elements serving as a blueprint by which concrete digital representation systems can be designed and constructed. It surveys and outlines technologies that can be used to enable the implementation of a concrete digital representation of factory system. With such a general system architecture, technology and solution providers can communicate with each other more effectively in understanding the requirements, needed technologies and solutions. Its architectural constructs and elements can serve as a higher starting point for system designer and implementers in conceiving their system design, benefiting from the ideas, concepts, approaches, and best practices from different fields from various industries, avoiding the labor of reinventing the wheel and the pitfalls of past mistakes. Offering the benefits described above, this digital representation system architecture will help to reduce the complexity, effort, risk, cost, and duration of conceiving, designing, and implementing such concrete systems. Successful implementation of such system will greatly reduce the effort and cost in creating and enabling smart manufacturing applications. Here, smart manufacturing applications, or simply applications, are what the system of digital world entities intended to enable. From the digital world entities, the application can access the data of the real-world entities, perform modeling, simulation, analysis, and other computational to gain visibility and insights of the operation conditions, states, and behaviors of the real-world entities. This data-driven insights can be then transformed into smart business decisions in accordance with the business objectives and operational and safety constraints. Any actions to be taken resulting from these decisions can be carried out through the digital world objects to the real-world objects. In the meantime, we have another project studying the connectivity requirements of digital representation for physical objects in factory environments. It will define the connectivity requirements of digital representation for physical objects in factory environments. Based on heterogeneous data, the connectivity requirements include high-speed protocol conversion, unified data modeling, and data access interfaces to meet the interoperability and interaction requirements between physical objects and the corresponding digital representations. So this is about the digital representation projects. And next, we're going to discuss the knowledge graph. And I will talk about how to support the standard-oriented and also machine-readable standards based on knowledge graph. The topic of machine-readable standards and smart standards is widely discussed in ISO and IEC. More than 100 IEC standards can now be processed by computers. An indispensable step as the interaction between human beings and machine intensify. Such machine-readable standards will be applied into the equipment of a smart factory directly without the translation of human beings. So this will have a very bright future for standards in smart manufacturing environment. Concerning a definition on machine-readable standards, we would like to refer to a definition that is discussed and accepted in ISO as well as in IEC, and is best described by the picture shown here. So if we're referring to level 2, this is called a machine-readable standards. And today we call the XML structure standard as machine-readable document. The machine or the software can distinguish between content and layout. And for level 3, and we identify specific granular elements such as requirements and tag them the right way in order to retrieve and extract them later, and to transfer them into other systems like requirement management software. And for level 4 means that we structure the whole content in a database format so that it can be directly accessed by software human intervention. So if you are interested in this topic, you might also refer to the IEC white paper published last year. It's about semantics in interoperability. In that white paper, it also introduced how to make these standards machine readable. And here in IEEE P2959, we consider knowledge graph as one of the possible methodologies to making standard readable to both human beings and machine. This standard specifies data and schema requirements for knowledge graphs constructed from published standards, which can be automatically machine readable. A knowledge graph, construction process, and performance metrics are specified. Application scenarios are also described at the end. So here, the architecture framework of the standard-oriented standard knowledge graph mainly composes of 5 layers: data layer, schema layer, standard knowledge structure layer, standard knowledge storage layer, and also the application layer. According to the different characteristics of standard data, we can divide the data into 3 categories: structured data, like table data, unstructured data, like text description of standard requirements, and also graph data. 2 kinds of special characteristics can be concluded for the standard document data. Firstly, the standard data is multimodal, which contains text and picture data. Second, the procedure data, for example, like the specific testing operation steps, often emerge in the standard documents. Based on the data layer, the schema layer aims to construct the concept model. Specifically, it defines the schema of standard-oriented knowledge graph, including entities, entity attributes, and relationships among entities. The system deals with 5 types of entities: standard file, standard object, standard terminology, standard requirement aspect, and standard process aspect, and 4 relations: standard association, terminology association, technical requirement association, and standard process association. Guided by the concept model created in schema layer, 3 kinds of information extraction technologies, like entity extraction, attribute extraction, and relation extraction, are utilized to obtain the defined entities with their attributes, value, and relations. Then the extracted triples data are stored in 2 kinds of database: a table structure or graph structure. Finally, 2 applications, standard template recommendation and standard conflict detection, are designed in this system architecture. So that finished the part 3, which we describe 3 technologies: machine vision, digital representation, and knowledge graph. Now we are going to move on to part 4. I will cover 2 projects in smart factory environments. One is about how to assess the maturity of a smart factory, and other is about defining the logistics inside a factory. So we will start from smart factory assessment. So why we need such assessment of a smart factory? Here we summarize 5 possible usage for such assessment. Firstly, it could help to assess a manufacturing factory's ability to initiate the digital transformation of its process towards smart manufacturing. Secondly, it will provide a set of coherent guidelines for assessing a manufacturing system and its management practices, identify improvement opportunities, and recommending technologies for adopting by manufacturers. Thirdly, it supports the manufacturing stakeholders to define their smart manufacturing vision, roadmaps, and strategic projects, and ultimately lower the entry barrier and reduce the risk of the transition process towards smart manufacturing. Fourthly, it allows companies to conduct self-assessments so that they can systematically and comprehensively align themselves with smart manufacturing. Finally, it also supports manufacturing SMEs in their progress towards smart manufacturing. So here in IEEE P2879, the working group is going to define basic terminologies, assessment process requirements, indicator metrics, assessment methods, and also assessment criteria for smart factories. As a continuation of smart manufacturing system architecture proposed by Chinese experts and adopted by ISO IEC GW21, Smart Manufacturing Reference Architecture, the Smart Factory Assessment Framework also tries to project the intelligent characteristic to the lifecycle system hierarchy domain. So as you can see here in this colorful magic cube, here is the intelligent manufacturing system architecture, and this is the origin of the assessment system architecture. To adapt the simulation of SMEs and some OEM factories, as you can see here, the company could choose the production column only to reflect the smartness of equipment, unit, and workshop layers instead of the whole life cycle. So you can always cut off this part, and instead of the whole life cycle assessment, most of the companies can choose only the production column to evaluate their maturity. In addition, if the factory does not focus on development of cooperation with other factories or ecosystem partners, they could cut off the metrics of cooperation layer. So as you can see here, this cooperation layers intends to say that the factories can work along with its partners and also with the third-party designers and logistic providers. But if you don't have that, you can also cut this off. Here, the working group also derived the initial consideration of performance metrics from both management and technology perspectives. In particular, for management-oriented metrics, the working group focuses on innovation efficiency, improvement rate, innovation promotion rate, waste drop rate, and decision support rate. So most of them is from the ISO 9000 point of view that take into the consideration of management, because smart manufacturing will not only influenced by the technology, but also change the way that management goes. And here also, for the technology-oriented matrix, the working group to consider the smart equipment coverage rate, data acquisition rate, network coverage rate, the utilization rate of the information system, and also the business integration rate, as well as data analysis utilization are considered. So here I just take one metric as example. The data acquisition rate equals to the total number of business data types that have been acquiring data automatically over the total number of business data types should be automatically acquisited. So according to this matrix, the working group tried to make all the things measurable so that the companies can always take control and track the influence of smart manufacturing they are leading to. And next, I'm going to introduce the smart logistics project. Smart factory logistics is the key to smooth and seamless supply chain performance. Such a system is engineered to suit different manufacturing environments and production setups, which improves operation flexibility. Using an advanced embedded IoT system, it could automatically recognize manufacturing demand in fluctuation. This will also allow supply chains to respond with better agility. With big data to uncover meaningful patterns, it will increase supply chain predictability and efficiency. So here in IEEE P2934, a standard for logistic operation process in smart factory is discussed and try to cover the aforementioned benefits. So this standard will define logistics operation process in a smart factory, including the process composition such as warehousing, package, shipment or transportation, implementation conditions, process quality evaluation, and process improvements. In addition, it defines methods for management organization, facility layout, equipment requirements, information systems, employee requirements, and emergency management and evaluation in a smart factory. According to the latest text of the standard, the working group defines the logistics process of smart factory, implementation guarantee of logistics operation process, as well as evaluation and improvement of logistics operation process, respectively. And also, for the audience to rate this standard, the logistics operation process specification of a home applicants and a 3C manufacturing enterprises are also given. Throughout these examples, the audience is able to discover how to design the division and layout of functional areas, and also requirements for personal, equipment, safety, and emergency situations. So lastly, I'm going to introduce two new projects and our future works. Firstly, is about the TSN gateways. And this project, we are going to work closely with IEEE 802 working group. So in this IEEE P2971 standards for the test requirements of a gateway supporting a time-sensitive networking in the field of industrial internet, the standard specifies general testing requirements for gateway devices which support TSN in the field of industrial internet. Requirements for protocol function testing, performance testing, security testing, and reliability testing are defined. And this working group is chaired by Dr. Cailian Chen, a famous and distinguished automation expert working in Shanghai Jiao Tong University. Another new project is IEEE P2975. It's about a standard for industrial artificial intelligence data attributes. This standard defines attributes related to industrial AI data that facilitates the classification, association, and mapping towards value creation using data. The attributes include, but are not limited to, data source, type, ownership, sampling, frequency, traceability, privacy attributes for modeling, sampling, shareability, and its use in AI algorithm. And this project is individual-based, so the experts are easy to participate in the discussion of the project. Finally, I'm going to discuss the future works of our standard committee. Comparing to the conventional manufacturing, smart manufacturing creates new value, has automation innovation, higher interoperability, brings security and trustworthiness concerns, comprehensive digitalization, information and knowledge intensify, and also computational intensify and human-centric. So there are quite a number of challenges. And these changes and challenges lead to individualization of products, services, and processes. And we have covered that somehow in mass customization project. Networking of systems, which results in highly complicated structure in the CPS. Although the digital representation and TSN networks are discussed, but this is just a part of the network of systems of the CPS. So more projects are welcome to discuss these changes. Value creation through new business models and subsequent services. Evolution of safety, security, organization, processes, and work design. And this is a project that we are lacking of in our standard committee, because here in smart manufacturing, we not only take consideration of functional safety, but IT security and data privacy, trustworthiness are most important. So we are welcome the audiences to participate in the study of these new trends. And finally, the impact on human productivity and innovation cycles. For smart manufacturing, this is not to replace the human beings by robotics, but to have a very friendly human and machine interaction environment. So here, how to improve the human productivity and also the machine productivity is the topic that we want to cover in the future. And in our future works, we welcome the experts and companies from all over the world to address these tremendous changes, as well as discuss and embrace the changes of smart manufacturing from the standardization perspective. So here, I have listed all the contact experts and information of all the working groups in our standard committee. If you are interested in any one of them, you are most welcome to contact them and join the discussion. We are looking forward to meeting you right soon. So thank you very much for everyone's attention. And I also want to sincerely appreciate the support of IEEE Computer Society, SAB, for giving such a good opportunity to present our works. Thank you so much.
Thank you, Dr. Shavi. Thank you. That was a great presentation. Quickly, just a reminder that the slides and the recording will be emailed out to everyone later this afternoon. Let's move quickly to the question answer. There have been some questions that have been answered already, so I'll move to the first one here. This is from Brenton Folk. Question is, it seems digital twinning is primarily necessary for representing a factory or other system to humans. but a ML model or expert system would not need such a representation to evaluate the production efficiency or efficacy of a factory. Beyond just visualization, what are some benefits of digital twinning of complex systems?
Thank you for the question from Northern Burger. And first, I will take the about the machine learning model. I guess this is in short for ML and expert system. So as you can see that the digital twin can connect real-time data from the physical entities. And this data will help to run new generated machine learning models. And also it will help to update or optimize expert system. So in this case, if we have some parameters which are initiated settings in the machine learning models or the expert system, and this kind of data will help to run new generations of that and then feedback to the physical entity to see its performance. And this will make iterations from time to time. So this is for the first part. And except from the visualization, here for digital twins, it just as I mentioned, it could analyze the real-time data together with the historical history that we have kept in the database. And also it will help to optimize the performance of the physical entity. For example, it can update or optimize the parameters of a process manufacturing equipment. And also, if the controllability permits, we can also predict the future. That is for the maintenance part. So we can predict that when will our equipment will shut down somehow. So we can do the maintenance in advance to avoid such case. So in summary, except from the visualization, we can do optimization, and we can also do a prediction, and also do some real-time analysis of the data. Thank you for your question. Richard, please. So I guess this is for the first one. Thank you so much. Rachel and Scott, are you still here?
I'm still here. I'm not sure. Maybe we lost Ritu's microphone, so I'll jump in here for the next couple questions. Let's see. All right, here's the next question. Mm-hmm. I guess you're aware of the German Industries 4.0 initiative.
Mm-hmm. Yes, of course.
All right, great. There is also certain cooperation between Industrial Internet Consortium and Industry 4.0. Among other things, they focus on digital twin. How are IEEE standards activities related to these efforts?
Mm-hmm.
Oh, okay. There's more? Hold on. How do you make sure yes. that there will not be two incompatible standard lines for the same thing?
Okay, thank you so much for your question. So firstly, I want to say that the vice chair of our P2806 working group is Dr. Shi Wanling. He's also the chair of the system architecture of the Industrial Internet Consortium. So he is also leading the discussion of digital twin in IIC. So in this case, we can always get the state-of-art information from IIC and try to include that in P2806. And also for Industry 4.0, as you may know that in IEC TC65, there is a working group 24 discussing the asset administration shell, which is the core technology of Industry 4.0. And we have a very close cooperation with them as well. Myself and Mr. Michael Hofmeister, which is the chair of this asset administration shell, and I have working along together on the digital twin and asset administration shell mapping and also the comparison. So in this case that we can also make sure that we will not have the duplicates or, in overlaps or complicated standards in here in IEEE and also in IEC or IIC. Thank you so much for your question. Scott. Thank you.
You're welcome.
Yeah, I can. Yeah, I can take the second one, the next one. This one is from Rod Wheeler. The question is, how does knowledge graph support MBSE modeling of systems?
Thank you for your question. In fact, I think that we haven't discussed this topic back in 2879. Here, the knowledge graph is studied for the published standard, which is the text. And for model-based system engineering, I guess I will pass this topic to them. And if you are interested, you can also contact the chair of this working group. Thank you so much.
Thank you, Dr. Shah. I think with that, we have all the questions answered. I don't see any more. So let me take this moment to thank you for your wonderful presentation, Dr. Shah, today. And I also like to thank all of you for attending. Before we close today, let me get a piece of information for the upcoming webinars. The IEEE Computer Society will be putting on 2 more webinars this month. On Thursday at 11 a.m. Eastern Time, Eastern US, on poor productivity habits and how to kill them from our Build Your Career series. And then for our Spanish-speaking attendees, we have a webinar on intelligent systems presented entirely in Spanish on July the 29th. In the month of August, the IEEE Computer Society will be hosting 2 webinars. The first will be on August 12th on lessons learned from an industry, government, and academic collaboration in educating secure software developers. And the other webinar from Build Your Career series on August 24th, focusing on emotional intelligence. Registration is now open, and you'll receive a link to register for all of these webinars in the email you receive tomorrow with the slides and recording. With that, thank you and enjoy the rest of the day. Bye.
Thank you, everyone. Thank you, Rachel, Scott, and Annie. And thank you, everyone. Have a good day.